So, we're going to introduce organic chemistry with a couple of ways that we can classify our compounds. So, as it turns out, we can classify our compounds um, by their structure, so what they look like. And we can also classify our compounds by functionality, like what can we do with them, or what can they do for us, kind of a thing, right? So, in this video, we're going to focus on classifying compounds by their functionality. And so I'd like to spend some time introducing what we call our functional groups. So this is by no means the end of the list. I'm going to share 10 different sort of categories with you, but there are many others. And as we get to each of the sections that deals with these functional groups, I will bring up some other functionality that can be made from these particular 10. But just as sort of an intro, I'd like to begin with the simplest, and that's how we're going to do it in the class as well. Is the second week we're going to introduce our hydrocarbons. So that's going to be our first category. And from the name, you can kind of just tell that these things contain only carbon and hydrogen. The special thing about carbon, it's in group 4, it has 4 valence electrons. It's neither here nor there in terms of electronegativity, right? So it has a tendency to share its valence electrons and form 4 covalent bonds. But it's cool because it can bond to itself and it can bond to other things in single, double, or triple bonds. So you can imagine this is kind of why we have a whole field of chemistry dedicated to carbon containing molecules, that is organic chemistry, um, because of the special bonding properties for carbon. And so we break our hydrocarbons down into a couple of different sections. The first section is we call saturated. And some of these terms are probably going to be familiar to you. You've heard of saturated fats and unsaturated fats, that kind of word. So saturated for us in organic chemistry means that all of the carbons are going to be, if they're not singly bonded to themselves, to other carbon atoms, they'll be fully saturated. That is, we're going to complete their octet with hydrogens. So saturated. And the first family of compounds that fall into this category are going to be called our alkanes. In general, the structure for an alkane is CN. So N is just the number of carbons that are actually in the molecule. And then H, 2N plus 2. These are going to be all carbon-hydrogen single bonds. So all sigma bonds. And an example of this would be something like, say, ethane. So for example, you could have a molecule like this. So I'm going to draw the expanded structure, of course, without proper molecular geometry. So we remember from our Gen Chem review, each one of these carbons has 4 groups bonded to it. The electron geometry is tetrahedral. Each one of these carbons is sp3 hybridized. You can also write this like this. So we have the expanded structure, we have the condensed structure, and then, this is probably a bad example, but I can show you a line bond structure. That's it. So in the line bond structure, each end of a line is a carbon, and then we imagine that the hydrogens are there to complete the octet. So that's it for ethane. The unsaturated hydrocarbons are broken into two categories. The first is going to be what we call alkenes. So unsaturations are where we're going to be taking away hydrogens when we make double bonds. So we're going to complete the octet for carbon with pi bonds, but you have to remove some hydrogens to do that, right? Because there's only 4 valence electrons on each carbon. So our alkenes have a general formula of Cn, N being the number of carbons on the structure, and then H2N. Notice the +2 is gone because we're going to be making a pi bond, or at least one double bond. So these have at least one carbon-carbon double bond. An example of this, well, we can stick with just the 2 carbon structure. Notice how we're going to put a double bond between the 2 carbons. We have to take away 2 of the hydrogens in order to do that. Otherwise, you'd have too many electrons around the carbon. And we took ethane and turned it into ethene. And this could be the condensed form. The line bond form would just look like that. Those line bond structures are a lot more useful when the molecule gets bigger. Alkynes are another family of unsaturated hydrocarbons. And in this case, we have Cn, H2N minus 2. So there's at least one carbon-carbon triple bond in an alkyne. So in other words, there'll be 2 pi bonds in that triple bond and the sigma bond, right? So sticking with the 2 carbon structures, each carbon is sp hybridized in an alkyne. So we have a linear compound, 180-degree bond angle, right? sp hybridization. This is ethyne. So notice we had ethane. So eth means 2, right? So 2 carbons. So ane means it's an alkane. Ethane, ethene, and ethyne. The common name for this you might be more familiar with is acetylene. So when we get into the section on alkenes and alkynes, we'll talk about their nomenclature. This is the condensed formula or the line bond structure. Typically when we're doing alkynes like this, the carbons are indicated because the line bond structure can get a little confusing to look at because that section of the molecule is going to be linear. We'll put little dots where the carbons are just to help you sort of say, oh, there's the triple bond and then those are the single bonds coming out. So those are our hydrocarbons. That's one category. In this category, I guess we could also include our aromatic compounds, but I'm going to give them their own number because they're special. They are not just simply fancy alkenes. So we're going to call these our aromatics. Sometimes they're called arenes. You may see that word. It's describing an aromatic compound. In this case, we have a conjugated pi system, meaning one after the other, the bonds. Every other bond is going to be a pi bond. And they are not they're not typical alkenes. There is an unusually high stability associated with these particular compounds. So for example, I'm sure you've heard of benzene. So in this case, and only this one time, I'm going to draw out the expanded structure for this. And you will quickly appreciate the line bond structure. Nobody wants to draw this over and over again. And you can imagine the more substituents we have on the molecule, the bigger of a pain it actually is. So see how we have every other carbon-carbon bond is a double bond? That is not a typical alkene. There's an unusual stability associated with aromatic compounds. They do not react the same way. In fact, they're pretty difficult to react. And so we'll have a whole section just on these. The condensed sort of structure for this would be C6H6. So this is benzene, by the way. The line bond structure, this is where you get to see your first appreciation for one of these, because the line bond structures for those other ones were kind of like, why do you need a shortcut for that? But it's a lot nicer to draw benzene like that than it is to draw the expanded structure. Again, the hydrogens are implied, and at each vertex we have a carbon. If you have heteroatoms involved, those are drawn in. Hydrogens are not typically drawn in. Our next category will be our alcohols. So alcohols have a general formula of R, meaning rest of molecule, and then OH. This piece is what makes them an alcohol. That's going to sort of differentiate them from other functional groups. The R groups can be the same, they can be different. It could be a big long thing. Just the business end of the molecule is the hydroxyl group. That's the OH there. So for example, I can have something like this, keep it small, methanol, right? Or I can draw this out to show you that it's the carbon that's bonded to the oxygen. But in the condensed formula, we usually write the carbon first and then however many hydrogens, right? And then whatever's hanging off. So here's your hydroxyl group. The R group is the methyl group. This right here is what makes it an alcohol. And as we move through the other functional groups, you'll see the difference. Like right now, let me show you an ether. So ethers they seem like they look like alcohols, but I'm going to replace the hydrogen with another R group. So I've got R, O, R, and R can equal R, or it can be something else. They don't have to be the same, in other words. So I could have a methyl group on one side and an ethyl group on the other, or whatever. Or I could have two methyl groups, right? So for example, if I want to draw an ether where I've got two different R groups. R is just, again, rest of molecule. So if I want to do like a methyl group over here, there's the oxygen, and then an ethyl group, Eth means two. So two carbons, right? So one side has one R group, the other side has another R group. This is not the same as an alcohol. So here I've got my methyl group, and over here, sometimes people will write like R prime or something to make them different. I'm just going to use different colors. That is not the same as an alcohol. So they have different properties, different intermolecular forces. You can hydrogen bond with an alcohol. You cannot hydrogen bond ethers. There's no hydrogen directly attached to the oxygen. They have very different physical properties. They behave very differently. So these are two totally different functional groups. And the next functional group would be the amines. And each one of these functional groups is going to get its own attention in this class. So we're just introducing them right now. We can have R for rest of molecule, and then we can have our what we call the amino group, NH2, or I can replace one of the hydrogens with another R group, or I can replace all of them with R groups. And we classify these differently. This is a primary amine, this is a secondary amine, and this is a tertiary amine. And they behave differently, right? In the tertiary amine, we don't have a hydrogen directly attached to the nitrogen, so tertiary amines cannot hydrogen bond to themselves, right? Primary amines have two hydrogens attached to them. Those things can definitely hydrogen bond to themselves, so the physical properties of these will change. So for example, keeping things small, we have methylamine. And that's an example of a primary amine. I guess we could do an example of a secondary amine. So we could do dimethylamine, or we could do trimethylamine. And again, the R groups don't have to be the same. So I could have something like a methyl group on one side. I could have an ethyl group on the other side. And I could have a propyl group down here. And that's still a tertiary amine, right? So these will have its own section on amines, but we classify these as primary, secondary, and tertiary. We also classify alcohols, but we look at those a little bit differently. We're looking at the stuff that's hanging off of the carbon that bears the hydroxyl group, and the alcohols, it's always going to be R and then the hydroxyl group. That's what makes it an alcohol. With the amines, it's nitrogen containing, but the nitrogen is directly bonded to the different R groups or hydrogens. Our sixth category are going to be our aldehydes. This is the first example of a functional group with something that's called a carbonyl functionality. So this has our carbonyl functionality. We have R for the rest of the molecule is going to be bonded to a carbon that's bonded to a hydrogen on one side and then has a double bond to an oxygen. This right here is what makes this molecule an aldehyde. because there will be other functional groups that have the carbonyl. This is what we're talking about. This is called a carbonyl, not a carbonyl, it's a carbonyl. And it's going to be a point of some pretty useful chemistry for us in this class. So that's going to be the spot where we usually do the chemistry. On an aldehyde, and we could have, for example, methanal, or in other words, formaldehyde. But notice that in that little case, H is the R group, right? We could have a methyl group over there, but as long as you have this, you have an aldehyde. Another functional group that contains a carbonyl would be a ketone. So this is going to look a little bit like an aldehyde, only instead of that hydrogen, it's going to be another R group. So over here, it's another R group instead of a hydrogen. So you could have a methyl group, the carbonyl, and another methyl group. That's acetone, or 2-propanone. So when we get into the nomenclature of these, I'll describe the difference. There's two different sort of ways that we can name compounds. We have another group containing the carbonyl called an ester. And esters have an R group, then the carbonyl, then an oxygen, and then that oxygen has another R group. So, and these R's, again, don't have to be the same. You can have symmetrical esters, asymmetrical esters. So, one that you could be maybe familiar with would be this. So see how we have the carbonyl, and then there's an oxygen, and that oxygen has an R group attached to it. This is ethyl acetate. So if you've ever used nail polish remover for fake nails, so nail polish remover for regular nails is acetone. You see that there. Nail polish remover for fake nails is ethyl acetate. These typically have fruity, kind of delicious sort of smells. Not everything in organic chemistry smells awesome, but esters usually smell pretty good. Another piece of functionality with the carbonyl group is a carboxylic acid. So if you're imagining that these are acidic compounds, you're right. We have R, we have the carbonyl, and then instead of in an ester where you see OR, here we have OH. And that hydrogen is our acidic hydrogen. So, for example, we have acetic acid, and this is the piece that makes it a carboxylic acid. The last category is another carbonyl containing functional group called an amide. We'll have an R group, we'll have our carbonyl, and then we have a nitrogen. And that can either have two hydrogens on it, or just like with the amines, you can swap out a hydrogen for an R group. The only thing you can't do this with is an alcohol and have it still be an alcohol. The second you swap out the hydrogen on an alcohol with an R group, it becomes an ether. So amides and amines, they're classified a little bit differently by the R groups that are actually, or whatever groups are on the nitrogen. So it can be, usually we put the hydrogen down here, or you have your carbonyl and you have your nitrogen, and you can have two R groups. So those are all examples of amides. So this right here, you may have heard of this before. This is dimethyl formamide. So that's the common name for this. DMF is a pretty typical solvent that we use in organic chemistry, or is a solvent that we use in organic chemistry. So that's an example of an amide. Another one could be like, so there's eth, right? That would have been ethane. 2 carbons, and then NH2. So this makes it an amide. It's the carbonyl and then the amino group, right? So that's ethanamide, or you may have heard of this if you ever took biology classes, acetamide. Other functional groups do exist, and we'll definitely cover them. Like we have nitriles, we have hydrozones, we have, imines, all that kind of stuff. But that's going to all fall out of chemistry that we do with these 10 sort of characteristic or basic functional groups. So these are sort of like the backbone. And from here, we'll do chemistry with each of these functional groups. And sometimes we'll produce new functional groups. Sometimes we'll make one of these from 2 others on this list. But this whole course is going to be dedicated to studying the structure and reactions of these particular functional groups.